Good morning, everybody. The last 3 lectures, we've looked at the tools that we would require to do structural analysis, and that is namely finding out the static indeterminacy, the kinematic indeterminacy or degrees of freedom, and then we looked at the virtual work method and the 2 principles that are used to solve various analysis problems, for example, finding out displacement and forces in a structure. Okay. So, today we are going to be starting off with what is known as the force method for analyzing structures. I am going to start off by looking at a truss structure to begin with, and then we will move on to beams and later frames. Okay. So, let us look at a simple truss. Simple truss where let us say that the structure is subjected to this kind of loading, okay, and so this is the loading on the structure, and this is the truss structure that you have. Now, if you look at this, what is understand that in the force method, the starting point is to find out the static indeterminacy of the structure. So, here we find out the static indeterminacy of the structure, and let us go through the steps. Number of members 1, 2, 3, 4, 5, 6. So, 6 members. Number of reactions 1, 2, 3. Number of joints 1, 2, 3, 4. So, if you look at the static indeterminacy, it is equal to number of unknowns 1 for each member plus the number of reactions minus the number of equations of equilibrium that you have, which is 2 per joint, and this is equal to 1. So, therefore, this is a single indeterminate structure. It is a truss which has a single degree of indeterminacy. Now, we go into the steps of how to use the force method to analyze. What do we need to find out? Here, let us just state the problem. The problem here is that I want to find out all the forces, the forces in all the members, plus I also want to find out the horizontal displacement of this point. So, I need to find out the horizontal displacement of this point under this loading. Okay. So, that's my problem statement. Evaluate all the forces in all the members and find out this displacement. Okay. So, this in essence is my problem statement. Okay. For now, let us forget about finding out this displacement. We will find out this displacement later on. Okay. Let us now first find out all the forces in all the members. Now, obviously, since it is a statically indeterminate structure, you cannot find out all the forces in all the members using just the pure equations of equilibrium. Okay. So, since you cannot use only equations of equilibrium, since it is statically indeterminate to the first degree, what you have is the number of equations of equilibrium that you have are 1 less than the number of unknowns that you have. So, essentially, if we can establish one other independent equation, then we can find out all the unknown forces. Okay. That is essentially the crux of the force method. So, how do we go about finding it out? The first thing that you do in the force method is you find out the statically determinate, statically determinate Bayes structure. So you find out the statically determinate Bayes structure. In other words, you take the structure, eliminate one of the unknown forces because it's a single degree of indeterminacy. So you have to eliminate one of the unknown forces. Once you eliminate one of the unknown forces, then what happens is now you have a statically determinate structure, because if you look at it, suppose in this particular case, what have we done? We have cut this member. This member we have cut. Once we cut this member, what happens? We know that the force in that member is 0. And since we know the force in the member is 0, no, let's look at it. Now how many equations of equilibrium do we have? We still have the same number of joints. So the number of equilibrium equations are still going to be 2 into 4. Okay. Only thing now is the number of members have been reduced by 1, because one of the members we know is going to have 0 force. So it becomes a statically determinate structure. So now the way we solve this problem is say that, look, let us take this problem, let us solve this problem. And to that we take the same statically determinate structure and say that let's look at this. In reality, this problem is really just a superposition of these two problems, where this force in this member, let me just number them here, A, B, C, D, A, B, C, D, A, B, C, D. So what we are saying is that from the original structure we get the statically determinate Bayes structure, where the member BD has been cut so that there is no force in the member, and we say that, look, this original structure is actually can be solved. You can find out the forces in these structures by finding out the force in these structures plus the force in all the members and reactions due to the unknown force in member BD. Now, what is the unknown force? We don't know what the unknown force is. So we assume that that is an unknown x1. So therefore, now suppose if you look at this, here there is no force. Here we have the force that BD actually has. So if you add all of them up, you will see that this is exactly this. Okay. So in other words, the redundant force for this structure, the redundant force is force in member BD, which we are saying is an unknown value x1. But suppose we knew x1, then we could solve this problem. This becomes a statically determinate structure because we know the force in one member. Okay? So this in essence is the basic idea behind the force method. You take the actual statically indeterminate structure, make it into a statically determinate Bayes structure by identifying certain redundant forces and putting them equal to 0 in the Bayes structure. Once you have the Bayes structure, then you add to the Bayes structure the structure being subjected to the redundant force. Okay. So now, and if you add the two of them together, you've got the original structure. So that is the basis of the force method. However, this is still an unknown. How do you find out this? Now let's see how we solve that. So let us look at the Bayes structure firstly, and let us analyze the Bayes structure. Here, assume that all the members, all 6 members have the same EA values. Okay. So let us look at this. So we have I'm looking at only the base structure now. The statically determinate where the redundant force is 0. Okay, and we're going to analyze that structure. Note that I'm going to keep this member there because the member still exists. It's very important to understand that the member still exists. It's just that in the statically determinate structure, we've assumed that the member force is 0. Okay, so let us now see what we can do. The steps, we are going through the steps. Sorry, this is A, B, C, D. So I have 10, 10, 10. And today I'm going to actually sit and analyze all the structure. So we're going to actually find out all the member forces by actually solving it. So let us go through it. If you look at it, now the first step here, what is the first step? First step, find forces in members using equilibrium. This is the first step. So let's do that. And here what I'm going to do is I'm going to be using the method of joints. Okay? And since I'm going to be using the method of joints, let's first find out the unknown reactions. Okay? Let's do the unknown reactions. And please, I'm going to just find out the reactions without actually writing down all the equations. I'll leave it up to you to write down the equations. Okay? Because by now you will already have taken a course in basic structural analysis, and finding out forces in trusses, beams and frames are things that you are expected to know. And so I shall not actually go around specifically solving statically determinate structures and how to find out the forces in them. I'll make an assumption that you know all of those. However, in this particular case, I will actually go about solving. So I'll go through the steps without actually writing the steps down. Okay. So first and foremost, these are the unknown reactions. So let us do sigma fx equal to 0 of the entire structure. That gives me that this is equal to minus 10. In other words, the direction that I am showing, it's actually in the opposite direction, 10. So I am putting down minus 10 because I have shown it in this direction. Okay. Now that gives me sigma fx equal to 0 gives me that. Now sigma fy equal to 0 gives me what? That this plus this is equal to 20. We know that. Okay. Now however, that still does not help us. So what I'm going to do is I'm going to take moments about point A of all the forces, and from that I can find out this value. Let's look at what are the forces. This does not have any moment. This has 10 into, by the way, remember that this is 4 and this is 3 meters. Okay. So what you have over here is, this is going to be 10 into 4 clockwise plus 10 into 3 anti-clockwise divided by 4, because this clockwise, this nothing, this one anti-clockwise. So this is going to be equal to 70 by 4 value, because 10 into 3 plus 10 into 4 is going to be equal to 70. 70 divided by 4 is 70 by 4. And now this, since this plus this is equal to 20, so this is going to be equal to 10 by 4. Okay, which is equal to 2.5 kilonewtons, and this is equal to 17.5 kilonewtons. Okay, so we've got the reactions for the support. Once we have the reactions for the support, of course I didn't really need to do that, but you know, it's a good idea. Now I can use the method of joints to find out all the forces and all the members. So let me start off with a simple one, B. Member B, note that this member, although it exists, I know that the force is 0 in this. So therefore, if I take sigma fx equal to 0, of member B, you will see that I'm going to get this is going to be equal to 10 kilonewtons. Okay, and similarly if I take Fy, I'll get this is equal to 10 kilonewtons. Okay, so I have found out the forces in these two members. In member BC, I have a compressive force of 10 kilonewtons. In member AB, I have a compressive force of 10 kilonewtons. Now where do I go? Okay, I can go, well, let me just go to joint A. I can go to any joint, but let me go to member joint A. Okay, if I look at joint A, and if you look at this particular one, if you study it carefully, you will see that, well, let's look at what is the force in this member. Okay, the force in this member is going to be equal to, well, if I take sigma fx equal to 0, I'm going to get force in AD plus the horizontal component of the force in AC. Okay, in AC, the horizontal component of AC plus the member in AD is going to be equal to minus 10. Okay, and similarly you will see that the vertical component of this member AC plus this 10, which is downwards, minus this 2.5, which is this way. Once you put it all together, you will see that this force, okay, let me forget about this, let's go here, let me go to this particular cross section. Here if you look at it, you will see that sigma fx equal to 0 gives me what? This has no force. And if I find out sigma fy equal to 0, you will see that this is equal to 70 by 4 kilonewtons. So compressive force, this is 0, and from that we can find out, actually if you go about it, you will see that this becomes 30 by 4 and 40 by 4, and so this is equal to a tension force of 50 by 4 kilonewtons. And now if you look at this particular situation, you will see that the equilibrium of this joint is satisfied automatically. And you will see also that the vertical of this is satisfied. So therefore, if you look at this, so what did we have? Let me write down the forces. FAB is equal to 10 kilonewtons. This is compressive. FBC is equal to 10 kilonewtons compressive. FAC is equal to 12.5 kilonewtons tensile. FCD is equal to 17.5 kilonewtons compressive, and member AD is 0 kilonewtons, no force. And note that I also have member FBD, which since I have cut it, I know that it's going to be 0 kilonewton. So this is not the true forces. This is the forces not in the original structure. This is not in this structure. Note that it is not in this structure, it is in this structure. These are the forces that I have found out for this particular structure, which is a statically determinate base structure. Okay. So I found out the forces in all the members. Okay. Now what is the next step? The next step is actually to find out the deformations in all the members. That's very important. We need to find out the deformations in all the members. Okay. And what are the deformations in each member? Please look at it. These are all axial forces. So what are the deformations in each of the members? The deformation in all the members are the deformation in member I you can find out is going to be equal to Fi, force, divided by A. What does the force divided by A give? The stress. Divided by E. What does that give me? The strain. The strain is uniform, so therefore integrated over the whole length gives me the axial deformation. So if I rewrite this, this comes out as Fi Li EAI. Okay, force in the member, axial force in the member, length of the member, the axial rigidity of the member. Okay, so therefore this way I can find out for each one what the corresponding delta is going to be equal to. And let me write down those values. Given these forces, I can write down that delta AB is going to be equal to 10. Note that I am going to put minus because tension is taken to be positive. So since it's compressive, it's going to be 10 multiplied by Li. What is Li? LAB. Let's look at LAB. What's the length of LAB? 3 meters. So it's going to be 3 divided by, note that I have said that all EA are the same. So delta AB is equal to minus 30 upon EA. Now let's look at delta BC. This is also 10 ton BC. BC. This 10 ton, and what's the length? Length is 4 meters. So this is going to be equal to minus 10 into 4 minus 40 upon EA. Let's look at delta AC. Delta AC, the force is 12.5 tension, so it's 12.5 tension. What is the length? AC. AC. Since this is 4, this is 3, you can see that and this is 90 degrees, this is the hypotenuse 5. Okay, the total length of AC is 5, so it's going to be 12.5 EA, and this is plus, so it's going to be plus 62.5 upon EA. That's delta AC. Then you have delta CD. The force, what is CD? CD is this. The force is 17.5 compression and the length is 3. So we can put that down as minus 17.5 multiplied by 3 divided by EA. So this is minus 52.5 EA. And finally delta AD and delta BD, what are they equal to? Since the forces are 0, 0, the deformations are also going to be 0. So I'm just going to write them as 0. The deformations are going to be 0. Now let me ask you this question. This is something that we always tend to forget about when we are doing structural analysis. Please note that you have to have dimensional consistency. Here I have said that all the EA values are the same. I have not explicitly stated the EA value. Okay, what are the units of E? Units of E are, as Newton per meter squared. Okay, they are normally more given in Newton per meter squared. Force per area. That is the value of E, because that is stress by strain. Stress is Newton per meter squared. Strain is meter per meter. No, strain does not have any units. Okay. Then what about the units of area? Area is in units of meter squared. Okay. So what is EA in terms of? It's in terms of Newton. Okay. What is force? What is the force in terms of? Well, I've given kilonewtons over here, but kilonewtons is nothing but 10 to the power of 3 newtons. So the basic units is Newton. And what are the units of length? Length is meter. So now when I write down F FL upon EA and delta is equal to FL upon EA. Let's see what I'm doing actually. Newton meter upon Newton meter. Units consistent. Delta, which is the displacement or deformation, has to be in meters. Okay, so we have dimensional consistency, and that is very important to know when you actually solve a problem. In other words, suppose you are given E in the standard form in SI units, which is GPa. What is GPa? Gigapascals. What's gigapascals? It's 10 to the power of 9 pascals. And what is Pascal? Newton per meter squared. So actually, when you say that something value is given in gigapascals, you have to multiply it by 10 to the power of 9 to bring it into Newton per meter squared. If you are given a force which is in kilonewtons, you have to multiply it by 10 to the power of by 3 to bring it into newtons. You need to bring all the parameters to the same basic units, otherwise you're going to always have a problem. Here I'm not doing that, however I am just trying to state here that you need to bring everything down. If you want to make F in kilonewtons, then EA also should be in kilonewtons. If you make this area into millimeter squared, then E also needs to be in Newton per millimeter squared. Consistent units will always ensure, and then your delta will be in millimeter, by the way. So as long as you are consistent, you shouldn't have a problem with units. Okay. So I have found out the deformations in all the members. What are these deformations due to? These deformations are due to the loads that are applied on the structure. Okay. So now, I have done that. Now what is the next step? Let us first go through all the steps and then I'll put it all together. Okay. So the next step is what? Next step is actually finding out the forces in all the members, okay, due to the redundant force. So in other words, what I am actually doing is finding out the forces in all the members due to the redundant force. So now I know that it will always be in terms of x1. So I can find out the coefficients by actually putting x1 equal to 1 and then solving the problem. So I'm going to solve this problem now. The next problem, remember that problem I had talked about? That this is actually this plus this. So for this I have found out the forces and deformations. For this, the second one, I need to now find out the forces. So let me do that. x1 equal to 1, and due to this x1 equal to 1, I need to find out what are the forces in all the members. Let's go step by step. Remember that this is still 4 meters, it's still the original structure. Okay, so this is 4 meters. What about the reactions? Look, this is a force that I am applying in a member. It's an internal force. So it's equal and opposite. So therefore, there is no net force acting on the structure, and therefore all the support reactions are actually 0. Because sigma fx gives me this equal to 0, sigma fy gives me this plus this equal to 0. Then I take moments about this point. Since these two are acting equal and opposite at the same point, this is going to be 0, this is going to be 0. That's not an issue. Okay. So now I need to find out what the forces in all the members are. Let's go about it. Let me first take joint B. In joint B, what is the force in this member? Look at it. The horizontal component of this plus the force in this member is going to be equal to 0. Then this, the vertical component of this plus the force in AB is going to be equal to 0. So from this I can find out that these are going to be equal to, this is going to be equal to 4 upon 5, this is going to be equal to 3 upon 5, okay. And now let's look at the other force. Let's look at this. If you look at this particular situation, okay, what's the force? I know this force. What are the two unknowns? I don't know the force in this member and this member. Well, sigma fx equal to 0 and sigma fy equal to 0 will give me. What will sigma fx equal to 0 give me? That the force in this member, the horizontal component of this is equal, plus this is going to be equal to 0. So if you do that, you will see that this works out to 1. Once you do that, then you can find out what is the force in this member, because the vertical component of this is going to be equal to this, and that way I am just writing down the values. You should be able to find them out. What about the force in this member? You will see that this will turn out to be 4 by 5. Okay. I found out the forces in all the members. So let me write them down. So that means force in AB is equal to 3 by 5 x1, because I put x1 equal to 1, and this is compressive, assuming x1 to be tensile. FBC is equal to 4 by 5 x1 compression. FAC is equal to x1 tension. Member CD is equal to 3 by 5 x1 compression. Member AD is equal to 4 by 5 x1 compression, and member BD is going to be equal to, well, that's the one that we've applied, so it's going to be equal to x1. So we have found out the forces in all the members due to an unknown force x1. Okay, and therefore if you look at it, what would be the force in the original structure? It would actually be, if you look at this, that the actual in the original structure FAB would be equal to 10 plus 3 by 5 x1, BC would be 10 plus 4 by 5 x1, AC would be 12.5 plus x1, CD would be 7.5 plus 3 by 5 x1. So this way, and FAD would be 4 by 5 x1, FBD would be x1 with the corresponding signs. Okay. So essentially, you see, I can find out the forces provided I know the value of x1. Okay. Now how do I find out the value of x1? See, I found out the forces. Here is where in the force method, additional equation to establish the value of x1, the force method, let's look at the original problem. Let's go back to the original problem. If you look at this, if you go back to the original problem, the original problem is this. Now what we've done is we have said that this is equal to this plus this. The only problem here is that everything is fine excepting that we don't know the value of x1. We need to find out the value of x1, and to find out the value of x1 we need an equation. How do we establish that equation? Let us go back. I've made a cut here. So when I make a cut here, under the action of these forces, what's going to happen to the cut? You see, all the members, the joints will displace, the members will deform, and because of all of that, what's going to happen? If this member moves along this direction relative to this, which is bound to happen because they all move independent of each other, there is going to become a separation. There's going to be an opening or an overlap depending on how B and D move. If D moves closer to B, there will be an overlap. If D moves away from B, there's going to be an opening. But the major point is that I cannot stop once I have made a cut from these 2 points which actually in the real structure are the same point. But once I have made a cut and I let the structure deform, these 2 points are going to get separated. Does that happen in the real structure? No. In the real structure, any point over here is not going to separate. They're going to move whichever way, and I'm going to separate. So what's going to happen? Well, let's have a look at the second point. When I apply x1, what do? Note that these two joints, I've applied a force x1 across the joint. Now, since these two are independent points, when I apply x1, they're likely to overlap. Okay? They're likely to overlap, assuming x1 is positive. They're likely to overlap. If x1 is negative, they'll pull apart. Now, understand one thing, that means in both these structures, what's happening? The point which I have over here, okay, are overlapping and opening up, depending on which is positive, which is negative. We'll find that out. But in the real structure, does that happen? Do the points overlap? Does any point overlap with itself? Can't. It's a continuous member. So what does that mean? In reality, in this structure, there is no overlap or shortening. So therefore, now you understand what we get? We get what is known as a compatibility condition. What we do is, we find out how much this has opened by. We find out how much this has opened by, and then add the two, and the two together have to be equal to what? They have to add up to 0, because the point cannot go anywhere. The point is stuck to each other. Okay, so that is the independent equation. So we need to find out how much displacement I get at this point, and we need to find out how much displacement I get at this point. Add the two things up, put it equal to 0, because this point cannot go anywhere. They cannot separate or overlap in the real structure, and therefore that gives us the additional equation that we are interested in. So essentially, understand that we have to find out how much this has opened by under this situation and how much this closes by under this situation. Okay, so that is the reason. Now how do I do this? See, this is a displacement. I need to find out a displacement. How do I find out a displacement using the method of virtual work? Use the method of virtual forces. Okay, what does it mean? Well, actually, since I'm trying to find out the displacement at this point relative to each other, what do? I actually apply a virtual force at this point and compute the work done. Okay, and the total work done has to be equal to 0. That gives me the displacement. Now, what is that force? Note that the force is exactly the same as the redundant force. So when I have actually solved this, I can assume that if I take this to be the virtual force, okay, what will be the forces in all the members? Well, I know what the forces are going to be. I've already got it. Okay, so therefore, if you look at it using the method of virtual force, what is the displacement at this point? The displacement at this point can be given by, I'm going to write down the virtual work equation here. The virtual work. What is the external virtual work? External work done by all the external forces. External, see, understand, this is the real structure, because I'm trying to find out the displacement at this point because of all these forces. So this is the real structure. So I need to find out the real displacements and real deformations. What are the displacements? Okay, real displacement corresponding to any force here. If you look at it, that you're going to get, what is the real displacement? Real displacement over here, if we look at it, is going to be equal to all these forces. Look at all these forces. These forces, what is the work done by these forces? The work done by these forces are equal to, let's go back, the virtual forces over here. This is the virtual system. The virtual forces undergoing the real displacements. Okay, so what are the virtual forces here? Virtual forces, if you look at it, the only virtual external forces are these reactions, which are all 0. So there is no external virtual, in the virtual force system, there are no external virtual forces. So therefore, the work done by the external forces, virtual forces, is equal to 0, because there are no external virtual forces. Okay. Now let's look at the internal virtual work done. The internal virtual work done is how much? What is the virtual force? The virtual force here is this reaction AB. So I need to find out what is that AB. What is the force in AB? 3 by 5. So 3 by 5 multiplied by the real deformation in member AB. What is the real deformation in member AB? Remember we computed the real deformation? It's this. So I'm going to put 3 by 5 multiplied by minus 30 by EA. That gives me the work done by the virtual force in AB, which is 3 by 5. Note that this is compressive. So the compressive force is going to be given by minus, okay, undergoing the real deformation in member AB, which is minus 30 by 9. So the internal virtual work contribution by AB is going to be minus 3 by 5 into minus 30 by 90. That's the force, the virtual work done by the real deformation in AB due to the loads undergoing the virtual force in the system. This negative implies that there is a shortening. This negative implies that there is a compressive force. Now let's go from AB to what is the next member? The next member is BC. So let us look at BC. What is the virtual force in BC? The virtual force in BC is 4 by 5 x1 compressive. So I mean, if we put a unit force, it's going to be 4 by 5. So that's going to be compressive minus 4 by 5 multiplied by the real displacement, which is minus 40 upon EA. So minus 40 upon EA. Then I'm going to add what else? The next. What's the next? AC. Force, tension 1. So it's going to be plus multiplied by the real deformation in AC, which is 62.5 plus. So this is 62.5 upon EA. That is member AC. Let us look at CD. Next is CD. What is the force? 3.5 into compression. So this is the virtual force is minus 3 by 5. What is the real deformation in CD? The real deformation in CD is 52.5. So that is minus 52.5 EA. Then we go to, next is, I have done AB, BC, AC, CD. So now I need to go to AD. What is it? Minus 4 by 5. The virtual force is minus 4 by 5. What is the real deformation? 0. So multiplied by 0. Then I need to look at BD. What is BD? 1. Tension. So it's going to be plus 1. What is the real deformation in BD? Real deformation in BD is 0. So 0. So what is the total internal virtual work? You will see that is going to be equal to plus 18 upon EA plus 32 upon EA plus 62.5 upon EA plus here you have 10.5. So 10.5 into 3 is 31.5 EA, and these are 0 and 0 plus 0 upon EA plus 0 upon EA. So the total virtual internal work done is equal to, what is it? 18 plus 30, 50. 50 plus 94, 144 upon EA. That is the internal virtual work done by what? By all the forces in all the members. And note that the external virtual work, if you look at it, is what? External virtual work done by all the forces is 0, but we have neglected one. What is that? That is, this is also an external work. And what is the external force? What is the work done by this force? This force is equal to 1 into what? What is 1? Into, note, what are we finding out here? We are trying to find out this overlap or whatever, the delta. Okay? So therefore, that is the reason why we applied the force x1. So therefore, this 1 into this delta is the external virtual work, and therefore once we put external virtual work is equal to internal virtual work, that is our principle of virtual work, because the total work done is 0. Okay, we get delta equal to 144 upon EA. So the overlap note that since we've applied this force, what we are actually computing is the opening up of the system. Okay, and therefore the opening up is equal to 144 upon EA. So we found that out. Okay, the next step now is to find out what? We found out how much this has opened up by. Now we need to find out how much this has, what is the displacement at this point. So for that, what is the real load? The real load is this. Okay, to find out the overlap, what do we need? We need to apply the same virtual force. So if you look at it, once we have found out the delta here, to find out the delta over here due to force x1, we have found out, note that these are now the real forces. So for these forces, we need to find out what is the displacement, the real deformation. Real deformation is equal to delta AB is, note that I've already done this, 3 into 3, so this is going to be 9 by 5 EA x1. Delta BC is going to be equal to 16 by 5 EA x1. Delta AC is equal to 5 upon EA x1. Note that this is negative and negative because these are compression. This is tension, so this is positive. And then delta CD is equal to 3 by 5 x1 into, what is the length? The length of CD. Length of CD is equal to 3 meters. So this is going to be equal to minus 9 by 5 EA x1. Delta AD is going to be equal to 4 by 5 compression. So this is going to be equal to minus 16 by 5 EA x1. And finally delta BD is going to be x1. So it's going to be, and what's the length of BD? BD is 5 meters. So it's going to be 5 upon EA x1. These are the deformations due to these. Now to find out, again using the same virtual work principle, you will get what? What is the displacement? The displacement is equal to external virtual work, all outside excepting for this, is going to be equal to 1 into delta due to x. See, this original one is delta due to the load. So this is delta due to load. This is delta equal to x. The internal virtual work is going to be equal to, if you look at this, the displacement multiplied by this. So we're going to get, I'm going to do this really fast, 27 upon 25 EA x1 plus delta BC, so it's going to be 16 into 4, that's going to be 64 upon 25 EA x1 plus next one 5 EA, so it's going to be 5 upon EA x1 into 1, so that's going to be 5 into x1. Then CD is going to be equal to the same thing, so it's going to be 27 upon 25 EA x1. Then AD is going to be 16 by 5 into 4 by 5, so that's 64 upon 25 x1 plus 5 upon EA x1 into 1. So this is my internal virtual work. So if I add all of those up in 25, what do I get? I get 27 plus 64, that is 91. 91 and there are 2, so it's 182. 182 upon 25, 182 plus 250 is 432 upon 25 EA x1. So if you equate the two, you get that delta x is equal to 432 upon 25 EA x1. So now I have computed delta L. If you look at it, delta L, I've got delta x, and what's the actual delta? There's going to be superposition of the two, because if you look at this, in this it's going to be the displacement in this plus the displacement in this, and that is going to be equal to, if you look at it, delta is going to be equal to 144 upon EA plus 432 upon 25 EA x1. And what's the actual delta? In the real thing, delta is equal to 0. From this you can find out x1 is equal to 144 minus 144 into 25 upon 432. So if you look at this, this is going to be equal to minus 25 upon 3 kilonewtons. I have found out the value of x1, the force, and once I find that out, I can find out the force in all the members, because all I need to do is for this plus this. Now I know x1, so I just need to find out, add all of these up, and I've got my x1. This in essence is the force method, and I hope that with this simple illustration I've been able to illustrate the basic concept of the force method as applied to a single static indeterminacy truss. Thank you.